Now let us discuss methods. Here, you may be realizing that when we have a function, we have optimality conditions. We can differentiate and find the optimum solution. So the question is, if I can differentiate and I can get the optimum solution, and with the help of sufficient condition, I can get to know whether the point is minima, maxima, or inflection point, then why I need single variable optimization methods. Here, you have to acknowledge that there are some functions which are not easy to differentiate by hand. When you differentiate, it is not easy to get the solution x star where the first derivative of the function is 0. In that case, we have methods to find the optimum solution for single variable function. So generally, these methods basically are divided into two categories. First is the direct search method. These kind of methods use only objective function values to locate the optimum solution. Another class of these methods are called gradient based methods. For those methods, they need first or second derivatives of the objective function to locate the minimum point. In the direct search method, we have bracketing method, and you can see that I have mentioned that these methods are called rough bounding methods. So for the function where we don't know where is the minima, so first of all, we have to bracket that minima between the range, say A and a B. So roughly bracketing that minima, we can use exhaustive search method or a bounding phase method. Once we bracketed the method, we have another direct search methods which are accurate bounding methods. These methods are called region elimination method. Under this region elimination, we have interval halving, Fibonacci series, and golden section search method. Then we have gradient based methods. And as you know, for gradient based methods, we need derivative information of the function. So in this category, we have Newton-Raphson method, bisection method, secant method, and cubic search method. We can also use single variable optimization method for quadratic approximation. Here we can calculate the point estimation method. We can also use for root finding. Now all these methods, they are based on the assumption that there exists only one optimum in the given range of x. So if we say that x lies between A to B, so we have to, in this particular range, only one minima will be lying. Let me begin with the bracketing methods. So first method is called exhaustive method, which you can see on the top. I will discuss this method graphically, and then I will show you the algorithm. Now this is iteration 1, and the function is plotted, and the range for x is given as A and a B, which I have shown in a different color. This method starts by saying that let us put x1 is equals to A. So we are starting from one of the bound, so that is on the left hand side. The second point x2 we find by adding a delta into x1. So this delta term will be defined by us. Once we get x2, then we get x3 after we add delta into x2. So in the figure you can see that we have x1, x2, and x3, and we have a delta increment from x1, then from x2. Now if you see those vertical lines, it will give me the function value at x1, x2, and x3. So let us compare them. Now looking at this curve, we can say that the function value at x1 is more than at fx2, which is also more than fx3. This means that we have to further move on the right hand direction. It means that when we are adding the delta, we have to move in the right hand direction. And since the since the objective function value is improving, then we keep on moving. So this is iteration 1. So this condition is there, which is I have written in a blue color. We continue. Now let's say this is iteration 2. In iteration 2, x1 is updated as x2, x2 is updated as x3, and x3 is updated as x2 plus delta. Now if you look at this figure, now this updated x1 and x2 are from the previous x2 and x3. And the new x3 we found by adding the delta value. Again, we have 3 function values. Here it is important to note that the function value at this new x1 we already calculated in iteration 1. Similarly, the function value of this new x2 we already calculated in the iteration 1. So we don't have to calculate now because these values we can save. Only we have to find the function value at x3. Now looking at this curve, we can say that the function value at x1 is greater than x2 and it is also greater than x3. So this is the same condition as we found in iteration 1. So we continue. Suppose we are at the iteration number k and we are updating with the same rule that x1 equal to x2, x2 equal to x3, and x3 equals to x2 plus delta. Now looking at these 3 points and looking at their function values, what you can realize that f of x1 is greater than f of x2 and f of x2 is smaller than f of x3. This means the function value at x2 is lying between the function values of x1 and x3. Whenever this condition comes, it says that the minima is bracketed, so we have to terminate. So this graphical representation will help us to know that how we can move from one of the bound from say left hand side towards the right hand side and bracket the minima. Now let us see how the algorithm works. So as I explained you, in this step 1, we have to say x1 equals to a, delta equals to b minus a divided by n, and n is the number of intermediate points. So these number of intermediate points has to be fixed by us. Then we set x2 is equals to x1 plus delta and x3 is equals to x2 plus delta. So that is iteration 1. Then we check the condition whether the function value of x2 is lying between x1 and x3. If yes, then we can say that the minima is lying between x1 and x3. We should terminate. If not, so that's why I have written else here. So we update x1 equals to x2, x2 equals to x3, and the new point x3 is calculated as x2 plus delta. And then we will go to the step 3. Now step 3 suggests that is x3 is smaller than b? If yes, we will again go to 2. If no, then either there is no minima between a and a b, or the minima is lying on one of the boundary point, either a or a b. From this, the minima point will lie in the range of x1 and x3. If we have to find what is the difference between the interval, so the final interval x3 minus x1 is equals to 2 delta, and that will become 2 times of b minus a divided by n. On an average number of function evaluation, now you can see that at step 2 we are doing only one function evaluation, that is at x3. Why? Because x1 and x2 the function value is already calculated. So on an average, suppose if we run for n number of iterations, so we have to calculate only n by 2 times, and extra 2 it comes from the step 1 where we need to calculate x1, x2 and x3. So the 2 calculations are extra, so that's why it is 2 plus n by 2. Let us solve a problem using exhaustive search method. Here I will be showing you some hand calculation. So let me define the function first. We want to minimize, say function fx equals to x square plus 54 by x in the interval of 0 to 5. Now, if you plot this curve, you will realize that the minima is lying at x is equals to 3. Since it's a simple function, I can always use optimality condition to find the optimum solution and the objective function. So you remember that the necessary optimality condition says that I have to differentiate the function and put equals to 0. When you differentiate it, it is coming out to be 2x minus 54 divided by x square. This means that the value of x will become 3. Now, once we find the solution, we don't know whether it is minima, maxima, or stationary point. Then we go for higher derivatives. So first we calculate double derivative. When we put the value 3, it comes out to be 6. Since it is already non-zero, so we stop it. Now here we perform double derivative. So n equals to 2. F double dash of 3 is greater than 0. So the point x star is 3 is the minima and the optimal function value is 27. So let us start with the step number 1. As you remember that the a will become the lower bound, which is 0, and b will become 5 because this is the upper bound on x. Then we set x1 equals to a0 and we have to set delta value. Let us assume that n is equals to 10. Then the delta value will become 5 minus 0 divided by 10, which is 0.5 now. Then the x2 value will become x1 plus delta 0.5 and x3 is x2 plus delta will become 1. Now in step 2, we compare the objective function values. So let us calculate them. So compute f of x1, which is infinite. F of x2 is 108.25 and the function value at x3 will become 55. Now if I compare them, you can see that function value at x1 greater than function value x2, which is also greater than function value of x3. So this means that the termination condition is not satisfied. So we should proceed to step 3 and then we have to update the value. So x1 become x2, x2 become x3 and x3 is x2 plus delta 1.5. Now in step 3, we check whether x3 is smaller than or equal to b. Since it is 1.5, so we proceed to step 2. That makes the first iteration. So first iteration is completed now. Now we have to again go to the step 2. So the new point is 1.5 x3. We calculate the objective function value. Just to remind you that the function value of the updated x1 and x2 were already calculated. Now, now we have to compare the function values. Again, the relationship f of x1 is greater than f of x2 and it is greater than f of x3. This means we have to continue. And then again, we will update x1 to x2, x2 to x3, and we will get the new point as x3 equals to x2 plus delta equals to 2. We'll go to the step 3 where we'll check whether x3 is smaller than or equals to b. Yes, we proceed to step 2. That is the completion of second iteration. So in most of the problems which we will be solving in the assignment, I will ask you to solve at least for 2 iterations so that you will understand how it is working. I just wanted to show you when it will terminate. So it just for showing you when the method will be terminating. So after 3 more iterations, you will realize that x1 will become 2.5, x2 will become 3, and x3 will become 3.5. If we find the objective function value, it will be 27.85, 27, and 27.68. Now, since the function value, what you can see that the function value of x2 is lying between x1 and x3, then we should terminate, and the minima is lying between 2.5 to 3.5. So that's why I have written x star belong to this. Now, one interesting thing you can see that this method has already found an optimum solution in terms of x2. However, it will never suggest that it is an optimal. It will always give you a range from 2.5 to 3.5. So x1 range between x1 to x3. Now here, if I find the accuracy for n equal to 10 steps, I can easily calculate by putting into the formula as 2b minus a divided by n. So if I put the value, I'll get 1. And that's why if you see the range of the minima, the difference between 3.5 and 2.5 is 1. The number of function evaluations, n by 2 plus 2 gives me 7. So on an average, that many function evaluation will be required to locate to bracket the minima. Now suppose what the currently the accuracy is 1, which is we believe is quite high. So let us see if we increase the accuracy as 0.001. So how many how many steps we needed? So if I use the formula as 2b minus a divided by n equals to 0.001, I'll get n as 10,000. Average number of function evaluation will become 5002. And the interval will become, you can see, and you remember that the optima is at 3. So what you will see, the difference here and the difference here, that if we have n value small, our accuracy will be small and we can quickly bracket the minimum. However, if we are looking for a higher accuracy, number of function evaluation will increase, but the advantage is that the range is so small and we can easily locate the minimum point inside this range. Now I am moving to the second method, which is called bounding phase method. Again, I will explain this method using these graphs. So let us assume we have a iteration number 1. Here in this method, we start with the point x1, which is an initial guess. This means that we will generate a random number between a to b, and then this will become our x1. So computer will help us to generate a random number. So let us see that x1 is written here. Once we locate the x1, then we find x2 and x3. What you will realize that x2 is x1 minus delta. It means that I have to go in the left hand side of x1. If I say x3 equals to x1 plus delta, it means that I have to move on the right hand side. So graphically you can say, now the purpose of adding and subtracting the delta is we have to find in which direction we should go, either on the left hand side or on the right hand side, where the objective function is reducing so that we can bracket the minimum. So let's see the condition written in the blue color. If function value at x2 is greater than equal to function value at x1, which is also greater than function value of x3, this means the function value at x3 is the least, then we should take delta positive. However, if you look the graph and you see these points, you can very well see that this condition doesn't hold. If this condition doesn't hold, means that I have to take delta as negative. So in my further iteration, the value of delta will be negative. It means that I will be keep on moving towards the left hand side of x1. Now let's take iteration number 2. Now here, once we decided that we have to move in the left hand direction by keeping delta negative, then the new point is found, which is equals to x1 plus 2 delta. Now the term 2 means we are jumping twice. Now here, looking at the function value, so x1 and x new you can locate on the x-axis, and further on this curve you can locate the function value at new point and function value at x1. Now you can clearly see that the function value at x new is smaller than fx1. It means that we have moved in the left hand direction and still the function value is reducing, so we should continue. So we'll go to the further iteration. So let's assume that we are at the kth iteration. In this kth iteration, as we know, whatever be the previous point will become x1 and x2 is x1 plus 2 to the power k. As you remember that, so you remember that delta was negative. So it means that we are jumping towards the left hand side. Now 2 to the power k suggests that every move we are actually moving with the power 2 to the power k. Now let's look graphically. So x1 is given on the x-axis, similarly x2. Now look at the function values at x1 and x2. We can clearly see that, which I have written in blue color, that function value at x2 is greater than function value at x1. Since we were moving from left hand side and eventually the function value has started increasing, this means I should stop. If I have to stop it, it says that the minima is lying between the point. So let's see how this algorithm can be written. So bounding phase method, how we can write? So step 1 says that we have to choose an initial guess, say x0. Then an increment of a delta. So this delta we have to decide. And we set k equals to 0. So k will be referring as a iteration number. Now you remember that thereafter what we do is we take minus delta and plus delta on x0 side. So we are calculating the value and comparing them. If the first condition satisfied, this means that delta is positive. It means that we have to move in the right hand direction. If the second condition satisfied, it means that delta is negative. So we have to move in the left hand side of x0. If nothing happened, then we have to go to step 1 and we have to play with our initial guess. Since it is random, we can always change it. If it is no, then if suppose we have decided what should be the value of delta. Now, since we have decided what should be the value of a delta, it can be positive and a negative. In step 3, we find the new point. This new point is depending on the previous point plus 2 to the power k delta. So as of now, the incremental factor or exponent is given as 2. We can take say e as well or other factor. Once we calculate, we have to check whether this new point is reducing the function value or not. So in step 4, we compare the function value at new. If it is smaller than the previous point, we increase the counter by 1 and then we go to the step 2. Again, we'll get another new point. We keep on doing till this condition is not satisfied. Suppose it is not satisfied, then we can say that the minima is lying between xk minus 1 and xk, and then we should terminate the algorithm. So what are the features? I'm repeating again. The algorithm begins with an initial guess. So a random point is generated between A and a B via computer. Then we find a search based on two functions, whether I have to go in the left hand direction or right hand direction. Thereafter, once we know that delta is positive or negative, we perform exponential search. So that's why this is 2 to the power k delta. We generally add into the point. Now what you will realize that delta has an effect on bracketing. If you keep very large delta value, bracketing will be fast. This means you can say that the minima will be lying these two values and you can find it very quickly, but the accuracy will be poor. It means that the difference between the 2 points in which the minima is lying, they may be very far. But if you keep a small value of a delta, this means that the accuracy will be better. This means the difference between the 2 points, the limits will be less. However, it will take more function evaluation. So usually the bounding phase method is faster in bracketing the minimum point than the exhaustive search method. So the same problem as we have solved with the exhaustive search method, we will be solving with the bounding phase method. So let's see how this hand calculation works. So you remember that the step one here is to initially find what is x0. So this is the initial guess, means a computer will generate a value for us. So let us assume that the initial guess here is 0.6 and the increment we decided is 0.5, set k equals to 0. Now we have to find x0 minus delta and x plus delta. So you can find, so it should not be computer, it should be compute. F of x0 minus delta is 540. F of x0 is 90.36 and f of x0 plus delta is 50.301. Now, if I compare these values, I can get to know that the function value at 0.1 is greater than 0.6 is greater than 0.1.1. It means that if I keep on moving towards the right, then the function value will be improving. So that's why we keep delta positive. Now in step 3, you remember that we have to find the next point, which is x1. So x1 will become x0 plus 2 to the power 0 delta, which is 1.1. And then we check the condition. Now, since the function value is better than the x0, we increment the counter and that finishes the first iteration. Now we'll go to the step 3 again. We'll find the point x2, which is x1 plus 2 to the power 1 delta 2.1. In step 4, we check the condition, means that we have to find the function value of at x2, which is 30.124. Now, since the function value is smaller than function value at x2 is smaller than x1, we keep on continuing and we increment the k by 1, so it will become 2. We'll proceed to the step 3, and this is the second iteration, which is over now. Now step 3, again, you remember that in step 3 we calculate a new point. So now it is x3 and this is x2 plus 2 to the power 2 delta. So you can see on the 2, the power of a 2 is increasing with the k. I get 4.1. Go to step 4, we check the condition. So first we have to compute the function value, get 29.981. Now this is function value at x3 is better than x2. We again proceed to step 3. The third iteration is over. So here my objective is to show you how it is working. So in step 3, we find another new point, which is x4 coming out to be 8.1. When we calculate in step 4, when we calculate the function value, it is coming out to be 72.24. Now what you will realize that the function value at x4, which is 72.24, is actually more than the function value at x3, which is 29.981. This means that we have to terminate, because now if I keep on moving towards the right hand side, the function value is increasing. So we should stop it, and the minima will be lying between x1 and x2 and x4. So you remember that x2 was 2.1 and this is 8.1. So for delta is equals to 0.5, the interval is 2.1 to 8.1 and the number of function evaluation is 7. Suppose if we set delta is 0.0001, this means that we are improving the accuracy of the method. You can see there is an improvement in the interval of x. However, the function evaluation is increased to double from 7 to 15. So the remarks are bounding phase method approaches the optimum exponentially, but accuracy may not be good. So 2 to the power k factor will help us to bracket the minima very quickly, but the accuracy is bad. However, exhaustive search method requires relatively more function evaluations, but the accuracy is good.